So we're here for teaching Java programming to the next generation.
Go ahead.
My name is Douglas Bays. I'm a senior software with Linden Incorporated that you probably never heard of. We're mainly a transportation company with about 30 subsidiaries that send freight all over the world. I've been doing software for about 15 years. I've been a FRC mentor, a First Robotics mentor for 2 years, and I've... Oh, okay. So I've been a FRC mentor for about 2 years, and I've been doing robotics for about 4 years.
So my name's Brandon, and I'm the president of my local robotics team, Team 2927. We call ourselves Omega Semicolon. It's absolutely random, but that's what makes it fun. I'm also a software and media engineer for the North American Eagle. They're working to break the land speed record with a converted F-104 or Starfighter. You can check them out at landspeed.com. And I'm also lead programmer for my robotics team. Not too terribly many people on our team, so we kind of all have to do multiple jobs.
So the quick disclaimer, First Robotics is not overseeing or responsible for this activity. They have let us use some of the media, but we just need to say that they're not overseeing this activity. So, go on.
So today we're going to cover a couple of different topics. First, we're going to start off with what is FIRST. For those of you that are completely new to this, don't know what it is. We're also going to cover some of the volunteering, the robotics games, the robots themselves, and then we're going to go in depth with the code, troubleshooting the robot, and then we'll have questions at the end for any of you that may have questions from our presentation.
So how many people here know what First Robotics is? So we got a fair number, okay. So you...
Next one?
Yep. Okay. So FIRST was started by Dean Kamen in 1992. If you don't know Dean Kamen, he created the Segway that rides up on 2 wheels that people ride around on. He's also created many medical inventions over the years. But what he saw was that high school kids going into college, there are a lot more going in to become, sports stars or other things, not going into technology. So he realized they needed something for kids to get them excited about technology. And so that's what they started it. First Robotics there's 4 different groups. There's what's called a Junior FLL, First Lego League. There is also what's called FLL, which is a First Lego League. And that's using the little Mindstorms, if you've ever seen those. And then there's FTC, which is the First Tech Challenge, which is a little bit bigger robot. It still uses some of the Mindstorm brains. And then there's the First Robotics competition. Now what we're going to talk about today is the First Robotics competition. That is primarily for high schoolers. If you have questions about the other ones, I'd be happy to talk to you about those afterwards. We'll talk a lot about... Well, everything we're going to talk about is mostly about the high school challenge, which is a really neat thing for the high schoolers. But the whole program is very neat. We'll take you to a website and show you if you're looking at something for younger kids to do also. Just to give you an idea of how big this is, the expectations for this season for all 4 of those groups is over 306,000 students involved, over 29,000 teams, 25,000 robots. They're going to need 57,000 mentors and adult supporters and another 63,000 volunteers to run events and keep things running. So if any of you have free time, we got lots for you to do. We need about 120,000 volunteers. The First Robotics competition that we're going to talk about has across, and these are worldwide too, mostly in the United States, but there's teams from all over the world. We'll have 2,700 teams, 54,000 high school students involved, and 60-some or 70-some events that will happen. And just about every state has an event. It's a really neat thing to go watch.
So one of the things that you can go and do is you can go to the FIRST website. You can access that by going to usfirst.org, and this has information on all of these different programs that he's mentioned so far. You can also learn about where you can go to volunteer. We'll talk more about that in a few minutes, but if you want information on these programs, this is the website to go and look at.
Okay, so real quick, if you came to see a robot, we had a little logistical problem. We'd hoped to ship one down. Unfortunately, Oracle won't take shipments of freight from speakers. They only do it for their exhibitors. The hotel also didn't do it, and then we thought, well, we'll bring down a little smaller piece. But we went and talked to TSA, and they kind of frowned on anything that had open wires and electronic pieces and everything. So we had a slight little logistical problem there. So we don't have a robot. We do have some pictures that we'll talk about. Okay. So if you do want to volunteer, this will be about the last time I'll really hit this, but if you do want to volunteer, you can go out to US First, and the regional contacts will put you in contact with the FRC teams. It is well worth your time to do. It's a really fun thing. You get to watch a lot of students grow and learn a lot of stuff, and if you're Java developers, you can teach these kids, and one of the biggest things these teams, the FRC teams, need is programming help. That's the one area they're always hurting for. So I really encourage you to go out and do that. I did want to warn you a little bit on what to expect. You are working with high school students. It kind of changes. You can have a year where it's like you have a really great group of really good programmers, and then you get another year where you're kind of all beginners and you're like teaching from scratch, which that can be really hard. You have to be careful. I had one year where I asked, I started the year out and I asked, how experienced are you guys and everything else, and they told me, oh man, they were really experienced, and we got in there and started programming, and I started jumping around in NetBeans a little, and all I did was like jump from one class to another, and they're like, what'd you just do? Well, come to find out, the programming they'd done was mainly in one class. Because a lot of times in the high schools, they really do a lot of their work in one class with just with algorithms and stuff like that. And if they use other classes, those are created. So just be aware, you really get a wide variety of experience when you go do this. Other things, kids don't have teamwork skills. They get teamwork assignments in school, and the schools always tell you they have teamwork. You really need teamwork for this event. It's a great way. First is a wonderful thing, all of the groups, for teaching kids teamwork, because they have to work together. What they have to build is bigger than any one person can do, so one person can't take over. A lot of the school assignments, I know for Brandon, he would get assigned a school assignment, and I would see him on Sunday night trying to make up the work of 3 other people who didn't bother to do any work on the assignment, and that's what schools would sometimes call a teamwork assignment. And so this forces them to really do teamwork. And it teaches kids about what a lot of us know about software engineering, or just engineering as a whole with a robot. It's not if it fails, it's when it fails, especially with robots, because they're going to be in that competition, and getting them to all come together when that robot just fails outright. And they just all jump in and do it instead of blaming each other is an awesome thing to see. And then the role of the mentor, the reason I want to mention that one is we all like playing with robots. The role, though, really is for us to teach, not to just jump in and do it all for them, which you always want to. But as a mentor, we want to teach people, and a lot of that has to do with asking people questions. Now, IT people are really good. We have a lot of really good problem-solving skills. We get stuff set on our desk all the time that you look at and go, how in the world am I going to do that? And those are the same skills you need to go build a robot.
So what actually constitutes these robotics competitions? Well, actually, they are like a big sports game. There's music, there's cheering, everybody is excited. Some of these students are absolutely bouncing off the walls with excitement. And it's absolutely great for those students that are not into sports, because it really is a game, but instead of a physical game, it's a game for the mind. So for those of you that have teenagers and you're looking for them to go to college after high school, one of the important things is, I know my parents are on me about this, is looking at scholarships, looking at schools. Well, one of the things that First offers is there's over $14 million in scholarships just for First students. 25% of the incoming MIT students last year went through this program. There are some schools that I know reserve up to 10% of their incoming students just for First. It's completely reserved.
So real quick, back up for a sec, please. So this is the Worldwide Championships this last year, and you can see, I mean, they're in a full-size stadium, and there's a heck of a lot of people in here. You've got one game going on here, and there's another. There's like 4 or 5 of these game fields spread out there. Now, so the regional ones aren't as big, but they're still in big areas. Ours last year in Seattle was in the convention center and had 100 teams, and I mean, these are pretty big events and really exciting to watch.
And just as a side note, Seattle has the biggest competition except for Worlds. Seattle is the one competition that has the most teams. So now what I want to talk about is the game that they introduced this last year. Now each year in January, we're given a challenge, a game. And we're given exactly 6 weeks to build and program the robot. Then we have to bag it up, ship it, and we cannot touch it until competition. That's part of the rules.
Sorry to interrupt for a sec, but so you think about that one, 6 weeks to build a robot. They have to manufacture the robot. They have to, they're doing welding and cutting and sawing and planning on building, and they have to solve a lot of different tasks, as you'll see in a minute. 6 weeks to do it. How many of us actually accomplish? If you get a project, it can accomplish something in 6 weeks. If we have a big project, a lot of times 6 weeks is just long enough for us to maybe have discussed it, to talk about getting started. And so it's really amazing what they have to sit down and go do.
So just to give you an idea of what this game is, it's played on a 27-foot by 54-foot field. And when you see it, you will not actually believe the size of this. It's incredible when you actually get to walk up to the field and see the true size of it. So just to give you an idea of what the game actually was this year, we're going to play the game video.
So this is about 2 minutes.
Welcome to the 2012 First Robotics competition and this year's game, Rebound Rumble. Rebound Rumble is played on a 27 by 54-foot court. Alliances of 3 teams each operate their robots from behind alliance walls at the ends of the court. 4 scoring hoops are located in each alliance wall, positioned at 3 different heights. A low barrier extends across the middle of the field. 3 bridges cross over the barrier. Each bridge has 3 positions, tilted toward either end of the field, or balanced level and stable on the central barrier. Rebound Rumble is played with compact foam basketballs. The objective is to score as many basketballs as possible in the hoops at the far end of the court. The higher the hoop, the more points it's worth. Robots can track the reflective vision targets above each hoop. This allows them to target hoops from anywhere on the court. The match begins with each robot touching their key at the far end of the court. Robots can be preloaded with 1 or 2 basketballs each. A 15-second hybrid period starts the match. During hybrid, robots can score basketballs using pre-programmed instructions. Every basket scored during this period gets a 3-point bonus. During the hybrid period, one alliance player can command their robot by signaling to their Kinect motion sensor. At the end of this period, human drivers step forward to take the controls. As the teleoperated period starts, teams command their robots to score as quickly as they can. Balls can be scored from anywhere on the court. The top of the key is a safe zone. Robots shooting from here are protected from interference by their opponents. But robots not touching this safe zone have to deal with defending opponent robots. As balls are scored, they are returned by players at the corners of the court. Robots can only hold 3 balls at a time. Once full, they drive the length of the court to score. They can use the bridge or cross the barrier to get there. Near the end of the match, robots drive onto their bridge and balance it for bonus points. 2 robots on their own bridge will get even more points. Each bridge can fit up to 3 robots, but it will be a tight squeeze to get them all on there.
Uh-oh.
In qualification matches, both alliances earn cooperation points if they work together to have red and blue robots balance on the center bridge. This is critical for the team's tournament seeding position. Cooperating will be just as important as winning if you want to be successful. Good luck, and we'll see you at the competitions.
So that's what they're given in January, around the first week of January, and they get 6 weeks to build a robot to go accomplish all those tasks. There's some cool stuff in there. You noticed where they were talking about the red and the blue having to work together to actually do it. So while they're competing against those teams, they're teaching them to work together.
So one of the main pieces you'll note is that, as described in the video, the field is split into two portions. It's separated by the barrier across the middle of the field. Now, part of the game is that you can either cross the field via the barrier or you can cross via the bridge. Now, both of these options present challenges, as in our default set of parts, we're provided wheels with a radius of 2.5 inches. Well, this barrier is 4 inches off the ground. So when you try to go across this barrier, your robot gets stuck. So this provides us provides somewhat of an issue. You can also try and cross via the bridge. The problem that you'll encounter there is that the bridge has incredibly slick surface coated across it. So when you try and drive up, you drive sideways and right off the side. It's not quite what you would expect. It's not nearly as easy as they make it look in the video. So again, one of the things that you'll note is that on the ends of the field, there's these vision targets right above the baskets. These are coated in a reflective tape, so what you can do is you can point a light at it and stick a camera right in that area, and what it can do is it'll actually be able to highlight those areas, and we'll go all more into depth with that in a little bit. So just some of the challenges encountered: crossing the center barrier, picking up balls is another interesting challenge that we encountered in this, as you're only allowed to carry a maximum of 3 balls at any one time. And part of what happens is it's rather hard to actually pick up these balls and process them through your robot quickly enough to be able to shoot them off. And one of the other things that some teams encountered is actually trying to calculate the shot. Since you have those vision targets, you can try and actually line up your robot, but you can also calculate it based on a couple different variables, such as you can set a fixed angle and adjust the speed to try and fire. You can also fix the speed, but instead change the angle. Now, both of these have issues at different points. We've realized this while running through some of our calculations. And then another option is that both of them can be changeable. However, this requires a little bit more complex calculations. And I believe we've run through the rest of them.
Just real quick. So the teams, kind of the structure of these teams is you obviously have several students. You'll have, usually you should have several mentors. So you're not like having to teach, figure out the whole shooting thing and all that. You may just be doing the programming. Or if you're really good at math and physics, then yeah, you might be helping do the teach the students how to calculate the shot. There's usually a pretty good team, and if your team gets lots of mentors together, it helps a lot, because there's just no way for any one person to know all about all of this. There's a good support structure for this.
So we want to talk about a couple of the different robots that were actually seen during the competition last year. So one of the first kinds you'll note is those that have a shooter mechanism higher up on the robot. But what happens is the balls actually enter through the lower portion of the robot, as seen down here, and they actually have to be lifted up here. Now, this entire robot was designed in CAD, and then it was custom built, and then they simply assembled all the parts of it. So the next thing you'll note is that you can try and get 3 robots on the bridge. Now, this was not nearly as commonly seen as you might think, because trying to get all 3 robots balanced is a rather tricky situation.
And usually the problem is that this robot here weighs, they can weigh up to 120 pounds minus the battery and the bumpers. This robot will weigh 130 by the time you add all that on, and this one weighs 80 pounds or something, which makes it really hard to try to balance 3 on there. So there were lots of little tricks you had to do, and you don't know who you're competing with. Every match you're competing with a different group of people, so you don't have like the same team all the time.
So one of the rules is that, or part of the game design field, is that there's a barrier in front of these different baskets. So what happens is you cannot simply drive up to the baskets and do a slam dunk, because the other rule states that you cannot extend any appendage from your robot more than 14 inches from the edge of it. So of course this limits you from simply having a mechanism that drops all the balls in the basket. But what some teams did is they simply raised a piece high enough up that when released, all the balls would simply fall into the basket, therefore allowing you, to have as close as you can to accuracy compared to a shooter. So again, mentioned during the game video is the cooperation bridge along the center, where a robot from each alliance will come onto the bridge and try and balance. Now this allows for more points, allowing both teams to move up in the scoring. Now this was actually taken in Seattle. Our team's robot is right here on the edge right here. This is the only time that all 6 robots were able to get on the bridges. This is the only time that happened in Seattle. And finally, you have the robot shooting at the basket target. So here you can see that reflective tape a little bit more clearly. So all you have to do is you light it up with a small LED light, and the camera is able to look at it and see that light and pick it out. Again, we'll go into deeper detail about those different vision targets in a little bit later with the code. So now we're going to take a look at some of the hardware that actually makes up these robots. So the main processing power comes from what we call the C-RIO. It's an industrial computer designed by National Instruments, and you can load a couple different firmwares on it. We'll talk about that when we actually go through setting up the robot. We also have our wireless bridge so that we can communicate with the robot wirelessly. We have power converters. We have our main power distribution board, and then we have 2 speed controllers sitting back here. Now these allow us to control how much power is passed back to these motors. Now these are rather small motors. The actual drive motors that you'll see on most robots are far larger than this. You'll also notice a digital in and out board that's connected to the main distribution board, providing control to the different speed controllers.
And so you see, we're just showing a small part of what you're going to program in a sec. Part of the programming we're going to look at First does a wonderful job of putting together the diagrams about how to wire all this together. If you don't know, and it's, usually you're going to be helping with programming, but if you get involved with this, you tend to, a lot of people get involved in a lot of different areas. And they put together great documentation, 1 about how to set up everything for the programming, and 2, like how to set up all the wiring and what the pieces are and everything. Even if you don't know anything at all, you can get started with it. Do
you want to pull up that video or that document?
Yes.
Should I wait for questions or ask during?
We're going to run up to probably right before we start the code, and maybe we'll take some questions there if that's all right. We have a whole lot of information on it, and want to make sure we get through as much as possible for people. So,
do you want to pull up the technical?
Okay, yeah, go ahead. It's actually the web browser is actually up, and so if you go out to FRC, well, we're actually on the FRC page, so we're going to go out to resources, and I can't walk this far. And then you go to technical resources, and we have this getting started with 2012 control system. This is just an example. They put together some great documents about how to do this. A lot of people are intimidated and think it's really hard to build a robot. It can be. I mean, you can get really advanced with it, and you can be really simple. So. And it's going to take a minute. So, it's almost there.
Yep.
There we go. We hope. Okay. So scroll down a little. Yeah. So you'll see step-by-step instructions on, here installing Java even, and all the pieces. They do a really nice job of putting this together so that you can do it you can make it all work. I won't say it's problem-free. It's like anything else with lots of pieces, but they do a really nice job of just putting it all together. So, and they do lots of documentation, which is really nice. Okay. So the robot, the C-Rio that we talked about, it's running on a CLDC 1.1 platform. I tried to find a little information about it. I know what pieces we use a lot, but it's you have a lot of pieces of Java missing, and think of it as Java 1.3, just to step back in time a little. So you have a thing, you don't have serializable. I've certainly found a few places where you're talking to the laptop, that would have been nice, but some of reflections not there. And then you go to the next one, Brandon. No finalization, and then limited error handling. If you get a non-runtime error, it just crashes the device. It has no Java native interface. If you're trying to talk to C, there's actually a C. You can actually do this in 3 languages. One's called LabVIEW, which is a visual language put out by National Instruments. The other one is you can do it in C++, and then you can do it in Java. So then you don't have any user-defined class letters. You don't really need it on the robot that much. And no thread groups or daemon threads. This runs on Oracle Squawk virtual machine. It's part of what they added on so that we can run Java on here. And then there's another piece called WPI Lib by Worcester Polytechnic Institute and Oracle built together. And those are the Java libraries that allow us, they build a platform on top of the Squawk VM that simplifies writing robots a lot for these kids. Because if they had to write all that low-level byte code, you'd never get through it in 6 weeks.
So now we want to talk about just a basic overview of how you even set the robot up. So of course, the first thing you have to do when you get all your parts, you have to put the basic robot frame together. You're not going to go anywhere with a pile of parts. That's kind of obvious, so we did not include it in our list. But when you actually want to go into programming, and first you got to set up the wiring. If this is not right, it's not going to run whatsoever. And one of the important things to remember is don't blame the developer, because quite often what happens is somebody miswires something, and because they do not understand the concept of programming, it's like a black box to them. They simply blame the programming. The programming does not work, or they say.
Sometimes it doesn't, but sometimes it really is the programming. But certainly, more times than not, it's like, oh, well, what port are you running this motor on? Oh, we're running on port 2. You're sure we're running on port 2? And you go look, and it'll be on 3 or something. So it's just something to be aware of.
Okay, you want to pull up the document?
Oh, that was the one we just pulled up.
Okay.
So go into the routers.
Yep. So the other thing that you want to do is you can, of course, run these robots wired. You just plug in an Ethernet cable and you can run it. But that's not always optimal. When you want to run the robot across the room and you want to actually see the capabilities of this robot, you want to be able to run wireless. So you need to set up a wireless router for it to communicate through. So one of the things that you'll note is that it's IPv4 only. And this is due to the capabilities of the C-Rio and part of the setup on the part of First, because there's very specific IP addresses that they assign to each device based on team number. And it's really important to follow the directions that they give for IP addresses. If you do not follow the directions for these IP addresses, the robot will not work. That is an absolute guarantee. And one of the things I like to do is I like to actually reserve the IP addresses, because what happens when a student decides to log on to your router and they automatically take the IP address reserved for your C-Rio. Well, now your driver station is going to attempt to ping their laptop, and you're going to be wondering, why the heck is it not connecting to my robot? So if you reserve the IP addresses for some of these devices, you don't have to worry about actually students connecting up with their own computers and messing it up. So next what you'll have to do is there's a couple different firmwares available. There's only one in particular for Java. So you'll need to flash the robot with this new firmware. And at that point, you'll be able to deploy your Java code to the robot. And you'll want to make sure that you check the connection lights on your driver dashboard. We'll go into more detail on that in a few minutes when we start up with the code. So there's just a couple of useful websites that you can go and look at. So the US First website, it's got resources and game and season information once it's released. It's really, there's all sorts of technical information that you can find there. It's great to go look there once a game's been released. First Forge, if you're programming in Java, this is the place to go look. It's got all the Javadocs and software that you'll need. It's also got the source code and other useful projects that you may find interesting. So, and then there's chiefdelphi.com. This is a large forum just concerned with First in general. It doesn't have to be a programming question. You can go look up if you have any questions on building the robot, how to wire it, or even how to be a good mentor or student. You can ask any sort of question there. You can also go look on National Instruments for different patches if you can't get Java working. We recommend, though, that you actually run through all the instructions provided before you go National Instruments. If you follow the instructions exactly and it doesn't work, that's the point where you want to go look at National Instruments. And the Javadoc is actually installed to your machine and when you install the different plugins to NetBeans. So real quick, we're going to take a look at that.
So while he brings this up, I mean, we kind of covered some stuff at a high level because we're trying to get to the programming part of this. So you know, when we're talking about the flashing the robot and all those pieces, lots of instructions for that in detail. We couldn't get anywhere close to getting all of it done in 2 hours. Now, so we're trying to kind of get to programming and talking about trying to work with students some on the programming.
So what you want to do is you'll want to go pull up our user folder. And in there will be a folder called Sunspot FRC SDK. Now this will not show up until after you install the plugins, of course. But once you've installed the plugins, you can go take a look under...
and that plugin is a NetBeans plugin that we'll talk about in a minute.
So you can go load up the doc folder, Javadoc, and then pull up the index.
Okay, so as you look at this, you'll find that there's about 3 sections in this. So we have the Java ME library, we have WPI Lib J, and we have Squawk, and then there's actually some other miscellaneous stuff down here. It really helps to go all through this. What you'll find is the packages kind of complement each other. So we'll take an example. We'll go down to math, and I'll get out of the way. Yeah, right there. So if you look at math, you'll see that it's under Java Lang math. So we got some math there, and then we go look at math utils, and we're under the Squawk library. So going through this Javadoc when you get into this with the first robots is very useful. And it's a lot of really good information in this Javadoc. Now, if you're building robots, the stuff that you're doing in First is actually very specific to First. But a lot of the things that you do are applicable to building robots with other things. I mean, you could build stuff on Beagle boards or Raspberry Pi or you know, all kinds of different things that can do a lot of this. It's just going to do a lot more of the low-level coding. Out on WPI Live is a lot of the source, and it can give you some ideas. There's also the ROS libraries that will give you a lot of ideas about how to get other robots going if you're just trying to put together robots and build something. So, okay.
So now we're going to talk a little bit about Java programming actually with the First Robotics competition. So Java was added in 2011, and it's a great language for students because you don't need lots of code if the students are not really experienced programmers. And again, as you mentioned, and you get a different set of students every year. Some have more experience than others.
So if you let the, you know, one of the things I think I said earlier is when you work with the students, give them ideas, ask them questions about why stuff doesn't work. You know, why didn't that arm move when you tried to do this? Try to work through with them. It's so easy to want to just step in there and do it for them. I guarantee you from a few years' experience that just doing it for them, they don't learn a thing. They'll look and they'll go, oh, okay. So you got to ask questions. You got to prompt them to kind of solve it themselves, and then they'll learn it, and it all clicks in their head. A couple other things. You know, we've all been coding for a lot of years, and there's these like set ideas in your mind about how that code should look and be, you know, formatted in there. And sometimes, you know, you get beginners or even some of your more experienced ones that if you point out every little thing that, oh, you need to move this here, and you need to move this here, and you need to do this, and you do that, and pretty soon it just comes like you're talking like one of those Peanuts cartoons where it's just like, wah, wah, and they don't hear what you've said. I found that in working with students that, point out something here and there, and then you'll get back to that code eventually and might point out a little more and point out a little more and kind of teach them incrementally as it goes along. But you do have to get over trying to get the code just the way you want it. A lot of times you can't tell them everything in hours. So, and the other thing is teach the kids about source control. They won't get it at first, but when you're at the competition and somebody has decided to go rewrite the robot and they wrote over the code, or somebody formatted the code that was on the robot the night before and you can't find the version they deployed that was working great yesterday, you're going to be really glad it's in source control, and it happens far more than you would. So teach them, we've just done like a simple SVN, or even just put it on Dropbox in data version so that you can go back some versions, but do something so that they have copies of the code.
So before we go into code examples, we'll have a brief period where you can ask questions if you have any. We've got all sorts of code examples to go through. We'll ask if you have any questions about the code examples, kind of hold those till the end. If anybody has questions, feel free to raise your hands.
How much did the original setup with you had the 2 controllers, the 2 motors?
These FRC robots, I think the initial getting started package, it's probably around, let's see, they give you a lot of stuff we didn't show. There's a whole bunch more stuff. It's a good about $3,000 for what they do. I mean, most of the teams, your first year to start out a team, I think it's $6,000 or entrance fee, or somewhere right around there. What you'll find though is almost every state has some sort of, well, they'll give you money to go do this stuff. I mean, that's, our state supports it. It supports 100 and some teams. They don't support all of it. We get grants. There's a ton of grants that you can get. We work with the groups that kind of organize the thing for the state, and they get all the money, or most of the money. There's lots of fundraising. I mean, this is a small business that these kids have to put together. I mean, we're talking about programming, but all the things they have to do. I mean, they're gathering the team, they're running the team, they're doing advertising, they're doing fundraising, they're doing CAD, they're media stuff, programming, welding, mechanical wiring. It's a business. And the top awards have very little to do with the robot, is the interesting thing. So they have like a chairman's award and some of that. Well, that really has a lot more to do with, I mean, the robots involve some in that, but they're looking at, well, did this team go out and take this information out? Did they do community outreach? Did they go out and talk to the community and get other people started? Did they mentor other FTC, FRC teams and FLL teams? There's a lot of things to it, and those top awards have very little to do with the robot. So
all those are factored into the final choice?
Yes. Any other questions? Okay. Oh. It is a kit. So every year when they have the competition, you sign up, and part of that sign up fee, they send you a starter's kit basically. And then you can continue to buy parts. You can also go online. There's andymark.com and some other places. You can buy just off the shelf stuff. There's limits to what you can do. Some things like you have to run your motors by using the C-Rio. You can't like run it by the Raspberry Pi or something like that. So there's some limits, but there's quite a bit you can actually do, and lots of parts you can buy. So yeah, there is a kit, and it helps get you started. So if you're a starter team, the kit's got just about everything you really need to get started and going. And then if you get real complex, you could be really simple, and then you can see some really complex ones. So.
Is the sponsorship basically by school, by individual, or by corporations? If I want to start a team.
Well, so we get sponsored by our state, our OSPI, which is office, our education office. We get some. We fundraise and go out to different corporations, which a lot of them are, especially in Seattle and lots of areas, are more than happy to put some money into technology. They need these students. We don't put out enough today, and they need these students. So, and then a lot of them do fundraisers, like they'll do a spaghetti feed and an auction or something else. Some of them make you know, thousands and thousands of dollars off fundraisers and stuff like that. A lot of donations, though, from a lot of big companies and that help out with this. So we've never really, you know, we can't always buy everything we want, but we've never like struggled to come up with enough money for it. There's a lot of money out there for technology. You know, in our state, there's a really good group, and most of them in the national U.S. First National, they work with a ton of companies, and they usually come up with money. Is what I'll say. It's not you're not struggling to you're not going to struggle terribly to do it, or you shouldn't be. There's something wrong if you are. So you're not out. You know, it's certainly good to go out and do fundraising. You really want to do that and raise some money up. There's some teams. I think somewhere in California that they have like a $80,000 budget or something, and they do it all by fundraising. I mean, there's that much support for these technology things, and it is really good for these kids because they.
Is there an Oracle team? Can corporate sponsor their own team?
Yeah, I know that there are people on that are members of Oracle that are on a team. I don't know if Oracle sponsors one. Is anybody in here? Yeah.
So is it against the rule to have like one corporation sponsor a team?
No. I mean, they can give money to do that. Yeah.
Are there any other questions before we continue with the code?
How much time a week do you spend?
Well, so the competition is about 6 weeks. We work probably, there's people there probably almost every day, except for Sundays. It doesn't mean it's the same people. And as a volunteer, you know, as a mentor, if you just have a day here and there, or you have, it's a little harder to fit you in if you just have a day here and there. You don't have to be there every day for 6 weeks. Because first of all, they have to build this robot. They have to build this frame. They have to figure out what they're going to do. Believe me, usually we're not actually making a robot move until around week 4, you know, 3 or 4. So you're not really, there's not a lot you can do sometimes. And where their real help comes in is towards that end. But I mean, if you have a day here and there, or you have 6 weeks, either way, we can find places, you know, something for you to do. Anything else?
This is a year-round thing, and it comes in for 6 weeks, and then before that you do all the fundraising and all the...
Yes, most of the teams run year-round doing stuff. So the FRC teams, that, you know, school just started. They usually they'll take a good part of the summer off, but a lot of them are still fundraising, or they're getting together and putting or you know, working on their skills like electrical and programming and all those pieces, or maybe they're teaching the FLL students what to do. What time do we have? 42. Okay, we're all right. Yes.
How many students do you usually have on a robot?
It varies. Our school is, I mean, we have a large school, but the time of year that they do that, it's a public school, and we have so many sports and so many other things that our teams aren't as big, and so we may run somewhere between 12 to 20 some students. Other schools come in there with 70 people.
On a single robot?
On a single robot, yeah. Mm-hmm. Some of the smaller robots, you actually have to create more teams. But for the big robots, the more people you have, the better. Because like I said, it is a small business. You've got a lot of stuff to do. You know, you're going out, you're talking to corporations to see if, you know, maybe they'll give you some money, but they're also, you know, you're talking to Subway to see if they'll sponsor a dinner one night because you're working, you know, you may be working several hours, especially during the later part of the season. There can be some long days, you're tired, but it's really fun when you get to the competition and, you know, that robot goes and does all the stuff you wanted it to do. So.
The regional competition? There's the national, or how does it work?
Yes, it depends on the state. Some just have a state competition. And then, like Seattle has, we have 3, well, Washington State has 3 regional competitions now. And then the winners of those will go on to a worldwide competition. Yes?
So, in addition to the number of students, how many volunteers are there in the team? And then if you could also talk about some logistics as well. When do you start forming your team, and how long does it take the team typically to learn the programming and all that? Leading up to the event?
Right. So it's best, like at the beginning of the school year, to get a team started, start doing interest meetings, and try to gather up new people, and start working then on some of the programming and stuff. We actually use, there's a smaller robot that's about 16 by 16 inches called the First Tech Challenge. It's not quite the same as this. It uses the first Lego. It's not using Java to program, but you use a C, kind of a, it's not complete C, but it's a good language to program robots. You don't have to teach people pointers and things like that. It just commands about how to drive. Explaining pointers to high school students is not a fun thing. And you don't have to do that in any of this. Avoid it if you ever think about it. But anyways, so you start at the beginning of the year and you'll start working on things like programming is a good one to start at the beginning of the year, especially if you don't have experienced programmers. If you have some experienced programmers, you may not do as much. They may already know a fair amount, and there's usually, like, we have workshops during the year that they can go to. Some teams really don't start until January, and they try to figure it all out in 6 weeks. And we've had people show up at the competition with a bag of parts. I mean, things just went wrong for them. And I know our school district, one of our teams, we have multiple teams, and one of our teams was basically like that. They ended up going there, and they just struggled that year. They lost a lot of people to sports, and they had a bag of parts, and all the teams got together and helped them build a robot. And I think that team that year actually got into part of the finals. So we were amazed. We were like, wow. But all the teams will come in and help. That's one of the great things about this is they teach you to compete, but they teach you to help. When we're at this competition, parts break all the time, and another team is going to be right there saying, "Oh yeah, I got a part for you. Here you go." And it's no, "Oh well, we're playing against you. We don't even know who you are." They'll be right there to give you a part and help you out, or they'll help. I mean, many times, Brandon helps lots of people program, several teams, and because that's one of the things people struggle with. They'll get there, and that robot won't be quite moving yet, and a little work, and they can have that thing moving along just like you want it to. So. Yes, actually, one of the teams in our area does build a full practice court. They happen to have a gym that isn't used anymore, and they got it for their robotics, and they build a full practice court. A lot of times, though, what will happen is, I think, can you bring up the picture with a target on it? No, oh yeah, okay, yeah, it's on here. You're right. Anyways, yeah. There was a picture that we saw of the vision targets with the baskets on there. Well, a lot of times all you do is you build that in with the baskets on there to work with, because we needed the vision targets to practice, because that's a really hard thing to fine tune. So you can't always simulate the whole field. That bar that goes across the field, that was polished aluminum. So you go try to drive up over it with your wheels, and you just slide half the time. I mean, they do it really, when they put these games together, somebody out there is really thinking them through, because there's all these little catches to it. You look at it and you go, "Oh, that's not too bad. We just got to drive up a ramp." First time we drive up the ramp, we go like that. And, oh, well, it's a little slicker than we thought. And, oh, yeah, we have 120 plus pounds of robot that's trying to push itself up this. And then, okay, well, now we got to put in some different gears, or put more, do 4 motors instead of 2, or lots of things like that. So, any other questions? Okay, so we will start in on talking about some of the programming of this. Okay, yeah, we're good.
And if you have any other questions, we're more than willing to answer those at the end after the code. So first thing we want to talk about is the development IDE. Now, currently the only IDE that is truly supported is NetBeans. Eclipse is still kind of in testing. It's not nearly stable, so it's not recommended. You can go and download the plugins from this URL. All you have to do is plug it right in to NetBeans. And one of the things that you'll note with NetBeans, the first time after you go set these plugins up, is you want to go load it up. You're going to go under Tools, Options. You're going to go under Miscellaneous. Where the heck?
FRC.
Okay. Yep. And you'll go under our FRC configuration. And what you'll want to do is you'll want to plug in the team number that of the robot that you're trying to deploy to. Because if you do not have the team number here, it will not be able to connect to your robot because it won't be able to calculate the necessary IP address.
So it creates an IP address like 10.29.27. Something, .2 to go to the CRIO. And so without that there, it doesn't know how to push your code out. It works a little different than NetBeans usually does.
So that means your team has to be pre-registered, right?
Yes, you have to have a team number to make all that work.
And
Yeah.
they'll set up all the IP address.
Now, one of the things you have to have if you're doing this, you have to have a Class A router. And so that means you can do some other, most home routers just want to do like, 192, 168, and it doesn't let you do 10. So that's something we've run into. Okay. So a lot of what we're talking about, I went about creating a bunch of examples and realized, well, it doesn't mean a lot because you don't have the robot that we had. But NetBeans, there's a bunch of examples in there that WPI has. So and they're on a nice open source license that says we can use them, and so I use a lot of those examples because there's lots of documentation out there. If you were to get into First and you want to go in your building trying to build the robot or trying to do some of this, there's lots of documentation out there. There's lots of discussion about it on the Chief Delphi website, and you can also ask people and say, oh, well, I'm trying to get this example going, and it didn't work, and people are going to know exactly what you're talking about. I do want to say, all the Java stuff that runs here is really thanks to WPI or Oracle, but these guys do a lot of the code that makes this work every year. So Brad Miller, Alex Henning, and Paul Mounstein, they get the WPI lib going, which is a lot of that's everything we're using basically, and they put all these examples out, and they did it in a nice way that we can use and share it. So.
We will show where you can access these different samples when we load up NetBeans in a minute.
And so now we're going to look at lots of code to do, a bunch of different things. So, yep. Okay, just a sec. So he's telling me I forgot what I was going to say, which is no surprise. Okay. Oh, okay, yep. So one of the things is when you have students working with this, always make two of them work together. They're learning, and so one person will sit down and do it, and you leave that one student there doing it, and they'll miss a bracket someplace, and they will spend 2 hours trying to solve a bracket. And I've seen this time and time again where I had two of them at least, not really paired programming, but just sitting next to each other looking at it. And one of them eventually in 10 minutes is going to point out, oh, you're missing this bracket, and you can go do this. So as you're working with students, just one of the hints is to kind of, get them to work together like that. Get a couple people to work together on this. It'll save a lot of time. And you as a mentor, you want to help them. You generally, it depends on the situation. You have to evaluate it, but you generally don't want to be over their shoulder the whole time. You want to kind of point things out once in a while, and at the beginning of the year, be teaching them, here's how you do these different things. And a lot of times, I'll write the code. So as I'm working with students, I'll write the code in there, and I'll show them how it'll work. I may make it work on the robot. I delete that code right out of there because I'm not going to do it for them. They need to figure this out. So I'll show them how. This is how you make this drive and make this joystick work, or this is how you do this in Java. And I'm going to delete that code out. Make them do it. They do not learn if you just do it for them. They tend to not learn it.
So as a volunteer, do you usually have a Kickstart class or whatever, like a Java primer, especially if you have a lot of coders or a lot of students that are not
Yes, we do. Yes. So we would start with. Last year we ended up with one of our other schools had a full team of absolutely no experience in Java whatsoever, which made it kind of interesting. You don't have to be a Java expert to program these robots. We're going to show you in a minute where you can make this robot move with just a few lines of code. But you still got to teach them about it. Here's how you create a method. Here's, it takes brackets. Don't teach them everything you know about Java. It'll be lost on them. But teach those common things and keep incrementing your what you teach them. But yeah, I do a Kickstarter class on that. We're doing, I know in November, we're doing for our Western Washington, we're doing a workshop that all the teams can go to where we'll be doing some robot things. And one of those classes is, nothing about programming Java, here's how to get started. And we'll take them from nothing to, trying to make that robot move in a couple hours. So.
Usually start like with NetBeans first, like an IDE piece, and then the Java?
Yes, I do. I just start them in NetBeans because that's what they're going to be using, and start them with a few simple, just a few dumb, just basic classes of basically the method probably only says system out println, right? And then here's how you call this method, and some of those things like that, really basic, because they don't need to know everything. And then as they go on, they become really experienced and they'll do lots of stuff. But then they start to get like him and they don't want any help anymore. But it's fun to watch what they come up with, because you're like, wow, I never would have thought of that. I would never have done that. There's so many things that you'll learn about that we would never do, and then you go, that was really a smart idea. So, okay.
So what we're going to start off with is we're just going to pull up NetBeans, and we're going to run through creating a basic project. Now, there's absolutely... Normally you would not have all these projects in here already, but since we're going to be demoing all these, we already have them loaded. So if you want to go create a new project, you're going to go File, New Project. And what you're going to find is not that. So you're going to start under FRC Java. It'll be a nice little category right there. And there's a couple different types of robots if you want to talk about that.
Yeah, so up here you'll see 4 items. We're really only going to talk about 3 of them. The other one's just kind of a holdover from the plugin that I just don't use as much. But we have a simple robot template project, which is what we're going to show a lot of code in the simple robot template project. Just because what I'm trying to show you is how to make certain smaller pieces work. Putting the code together for a full robot that does a whole lot of things, we'd be paging through a lot of different code. So we just use a simple robot to show things. It's a great one to just get something moving. And the iterative robot, it is a little more complex, not much. The command robot template that we have up here is actually what I would recommend is the way to build robots with your students. And there's some nice helpful things that in it. Yep. Thank you. The command robot, there's a lot more classes and pieces to it, but it deals with stuff like threading and some other things, so you don't have to try to teach kids how to write threads. Because remember, you're in Java 1.3, and the threading gets really ugly quickly, and especially you're sitting on a whole bunch of static objects. Because in a robot, I only have one drivetrain. I never have more than one drivetrain, and so you've gone and you've taught these kids, we're doing object-oriented programming, and so you got to do new, and you got to do these things, and then but you can't do that to the drivetrain, you can't do that to your joysticks, and you can't do that to all these other pieces. But anyways, those are the robots we're going to talk about. So, open that up again real quick, so we talk about the samples. So if you go down to the down here under samples and NetBeans. You'll see right here that you have FRC Java, and this is part of the plugin that comes with it. There's a whole lot of different robots here. Some of these are some older stuff here. There's encoder demos, there's enhanced I/O, and Connect, and all kinds of different things. And those are great. Those, when you say new, that creates the whole project with the code in it and everything else. Is some great samples there. Like I said, there's also documentation on FirstForge that gives you, oh, you want to do a gyro, here's how you do it. And it'll give you the pieces of the code. So, okay.
So now we're just going to start off with a basic robot move. Now this robot, all it's going to do is it's going to go forward for a certain distance, and then it's going to turn in one direction, and then it's going to turn and go the other direction. So there's a couple different methods that'll be created automatically when you create your simple robot. So the first one that you'll note is robot init. This is basically where you define all your different drivetrains, joysticks, sensors, all those different things that you want to actually create for your robot. This is where you're going to define them.
And so when he's creating, you'll see that we're creating a drivetrain right here. And we pass in a couple things. Well, on one of those, when I showed the electrical parts, there's a little blue board there, and basically there's just, you'll learn as you go along, but there's a wire that plugs into port 1 that's running off to a motor controller, and that motor controller tells the motor how fast to go. And so, I mean, it's as simple as all we got to do is say, well, plug in these 2 motor controllers.
So during the competition, there's 2 modes. There's one called autonomous, and there's another one called teleop. And teleop we're going to reference as operator control in our code. So autonomous is basically the point where you have a pre-programmed set of instructions and the robot simply runs through them. The robot's given 15 seconds, you run through the instructions, and then the student drivers can step forward and control the robot from that point. So for this example, we're just going to work through autonomous because we simply want our robot to run a set of pre-programmed instructions. So we've already defined the drivetrain above, passing in those two motor controllers. So what we're going to then do is we're going to say drivetrain.drive 1.0, 0.0. And what that's telling us in the robot is to move forward at full power, but do not turn at all. So the first variable simply controls the speed, the second variable controls the turn of the robot. And we're going to let that robot run for 2 seconds before we execute our next command. So the robot will run for 2 seconds, at which time it'll take over and it'll stop moving forward, but instead turn 100% to the right. But one of the things I want to note is that this is one of the cases where when you think you're going to turn right, you turn left, which normally would make absolutely no sense. But what sometimes happens is when people go wire the electrical, they don't understand the concept that the motor controllers have to be plugged in a certain order. Not only do they have to be plugged into the right ports, they have to be plugged in the right order, because if you put them backwards, what'll happen is your robot will turn left when you think it's supposed to turn right. And that is a whole nother headache that you really do not want.
But you'll see here that we created a drivetrain, and we started making this robot drive with just lines of code. I mean, they've done a great job of the libraries they put together. And the nice thing is that like the WPI Live, the source is out there. You can go pull up the source and see what they did, which is, you guys will be really interesting. But obviously you don't want to teach students about, well, pack the bytes together and push it over this way and flip this byte is not a fun thing to try to teach, but this gives them a great grasp on, oh, here's how to program, and there's plenty here to get really complex if when they want to. So.
And the final command that you want to pass in is drivetrain.drive 0, 0. All that tells it is to stop the robot, because if you fail to pass this variable in, what will happen is the robot will continue running and sometimes destroy the room, which you really do not want. This is the point where the stop button usually stops working.
And the first time you start a robot up, since the kids should have done this, first time you do it, clear it out. Clear a big area before you turn that robot on and do it. We've had them run smack into the walls, 120 pounds. It will hurt somebody if you're not careful, and somebody gets doing something and they just don't realize what they're doing. And everybody's trying to be helpful, so it's something to really be careful with. Okay.
So now we're going to show a short clip of a simple piece of code just being deployed right to the robot.
So it looks like this is going to be a little hard to see, but we'll kind of try to talk about it. We're going to show several videos that show the dashboard and some of this other stuff. And you'll see this is deploying code to the robot. And it really runs through, it's loading some stuff on the squawk, it's finding the network here, and most of them are not text, they're visual things we can see a little better. But it's rebooting the C-RIO here. And the reason we did these was, since I can't bring a robot, I wanted to kind of show you something and give you a little bit of an idea of some of what's happening. So I took the screenshots of NetBeans and the driver station. And so it kind of boots through a bunch of stuff. It's doing some FPGA software stuff, and most of it doesn't mean something, but if you run into a problem, it'll tell you down here, and you start to learn more and more about all the pieces. And it comes down, it doesn't really say it's done, it just says, oh, well, here, in this case, we didn't override a couple methods. You don't have to. There's defaults in there. It just tells you, whoops, we lost.
Yeah.
Okay. So it doesn't really say it's done, but what you'll learn is, oh, well, when I get down to this method running, consider providing your own. It's been loaded onto the robot. Well, look how we're going to start that up on the driver station in a minute. So. Just minimize, don't close.
Yeah. So the next example we're going to go through is we're actually going to add joysticks to our code. We're going to let the students actually drive the robot with the joysticks. Or you can just have them program and you drive. That's
So as he said before, there's an autonomous period, which is usually about 15 seconds. You know, you get one of these big robots trying to shoot a basketball and all that. It's pretty hard for these kids to, you know, a lot of them do get it. They get extra points for it, but most of the competition is just driving with joysticks. And you'll have a camera. You can have a camera on there and some other stuff. And they're competing against each other, so they're, those robots are just going crazy.
So in
Do you get feedback as to your position? And like you're saying, robot moved this far, but you get to know where it is?
Well, one, they can see where they're at, but the other thing we're going to look at here in a minute is some sensors. So we're going to do just walk through some basic sensors about, oh, well, I can set up something that does distance, and I can set up something that tells me a gyro and accelerometer and some stuff like that. And so we're kind of building up to where we get to a bigger robot at first here. So the answer to your question is yes, but you have to build it all.
So what we're going to do in this piece of code is we're going to add a couple new elements. First thing you'll note that we add is left joystick, right joystick, and shooter motor. So the other thing that we're going to add is now we're going to pass in 4 different motors. What you can do is you can actually chain 2 motors into a single drivetrain, which allows you to put more power behind multiple sets of wheels. And it's very nicely encoded so that it'll automatically take care of all of that movement for you. It takes a lot of the hassle out of it. However, this comes back to my point of you want to make sure that you have all the wires plugged in correctly, because if you have them backwards or something's wrong, what can happen is you can ruin about probably $150 worth of hardware in under 2 seconds.
So you have 4 wheels, you got 2 up front, 2 in the back, and if the back are turning forward and the front are turning backwards because you got confused, you now just caused a major problem in what it's trying to do. And one of the things you don't see that this actually is doing for you, and the reason that you have to get these ports just right is that you have to realize your motors are facing out this way. So 2 are going forward, but 2 are going in reverse actually.
And then we're also going to define the 2 joysticks as passed into USB port 1 and USB port 2. This is actually quite simplified because you don't actually have to know all the individual USB ports on your computer. It'll just detect them for you. And then the shooter motor is going to be defined as PWM port 5.
So up here we've just defined that extra shooter motor that is going to power. So on this year's robots, you have a robot, and then up towards the top somewhere you're going to have a motor that's spinning, and you're going to push the balls all the way up to it, and that's kind of your last thing where you got to have a really fast motor that's going to push that ball up and out and into the basket.
So now for this code example, we have nothing autonomous because we want to completely control our robot by joystick. In our operator control, all we've set while is enabled and is operator control. Because what happens is we want it to continue to loop through our code. If we simply left this out, it would only run through this set of code once. So what this allows us to do is it checks to make sure the robot is still enabled and it's in the current mode. Therefore, you don't have to worry about once the game is stopped or you hit the stop button, your code stops correctly. This is just kind of a safety feature so that you don't completely destroy your own robot. So there's 2 different main types of drive that you can pull in. There's what we call arcade drive, which is simply using a single joystick. You push forward to go forward, left to turn left, right to turn right, and so on and so forth. Tank drive is the concept of using 2 joysticks, where the left joystick controls the left side of the robot and the right side joystick controls the right side of the robot. And so these are 2 different types. I do not recommend using them both at the same time because your robot will do terribly screwy things. So normally you would want to comment one of these out.
Yeah, you wouldn't have both. We did this to show you can have, you pass in a couple joysticks. There are some other drive types that you can do. We don't really talk about that. If you're into those, you'll have you have people that'll know something about it. There's one that's called Mechanism that basically your wheels are you have one set of wheels that are about like a 45-degree this way, and another set that are a 45-degree this way, and the wheels have little wheels almost on them, and so that robot can go at an angle or sideways almost. Is kind of a cool thing, but that takes a bit of programming to make all that happen and make it actually work right.
We've also programmed in a couple of different buttons. So what this will allow us to do is if the trigger's pressed on our right joystick, it'll start up the shooter motor and it'll set it to full speed. Now if we press button 4, now this is different for just about every joystick, so you do have to check with the specifications on it. You can check this inside of your operating system though. It'll shut the motor down. One of the things that should definitely be noted is that if you use the same button to turn it off and turn it on, this whole program is cycling through several hundred times within a couple of seconds. What happens then is basically you turned the shooter on and off several hundred times in just a couple seconds, which is truly not recommended. So what a lot of students will do is they will use a timer delay so that when they press the button there'll be a slight delay after pressing the button before it proceeds with the code through the next cycle. Of course, there's better ways to do this, but that is the common way that a lot of students do it.
And for demonstration purposes, we put these buttons are right here in our main operational control, but you have to remember as you add functionality to this robot, say you add vision, or maybe you have an elevator lifting something up, or you have an arm that's doing something. This all takes time. Well, if those other things are taking time, it may not detect your button click. And that's where, if you were doing a simple robot, so go back up to the top, please, Brandon. When I talk about the simple robot, further up, you'll see that we talked about those templates earlier, and we had the simple robot template. Well, this extends simple robot. And it just has these 3 sections, basically, the robot init, the autonomous, and the operational control. So if you're doing a bunch of things and something takes like a second, well, you could click the joystick and it won't detect it because you're looping through it. And so that gets into, well, now I'm in this simple robot, and okay, well, I want to catch this, but it depends on what the robot's doing. So I might be able to write a thread that, it might detect it, but it takes some tuning. But then now you're trying to teach kids how to write threads and keep everything synchronized and everything else. And that's where we're going to look at the command robot that it solves some of those problems so that you don't have to deal with that. But it's just something to keep if you start, you start getting into this and doing this. There are some kids, I've seen some incredible code that comes out that they'll do it on like a simple robot, and they'll be launching threads and everything else. And the role of the mentor, it's different to every team. Some mentors that they do a whole lot. I definitely am one that believes you need to teach and not do it all. But part of First, there's nothing that says you can't. Part of First is that what they want is students working side by side with engineers, and that's that's the goal, and that's so. However we do that. So
the next code example that we want to go through is called the Iterative robot. This is a little bit different from the simple robot.
So real quick, can you guys at the back see this at all, or you see the text? You can? Okay, good. Go on, I'm sorry.
The Iterative robot is a little bit different. So there's what we call init commands. In the simple robot, there's only one init command. This init command is simply run once. In the Iterative robot, there's an init method for the entire robot, and then there's also init methods for autonomous and also operator control, which is not seen here. We also have what's called periodic. This is the slow loop. This is used if you want to update your dashboard, which we'll go into a little bit more in a few minutes, and other functions that don't need to be updated nearly as fast, but you want to run in the background. And then we also have what we call the continuous loop. The continuous loop is used for running motors and other functions that you want done really quickly and constantly updated.
So you'll see that we started here in the telop init, which is where we set up this get watchdog, and we don't really have to set up the watchdog. Part of that's enabled behind the scenes, but basically what that watchdog object does is if the robot loses connectivity for or you don't do what's called feeding it, which down further in the code someplace we say get watchdog.feed. If you don't do this or it loses connectivity, the robot stops. So if you're out doing something, it's not, it gets going and loses control and it'll stop. It's a nice safety feature. But we set it up in the init, so when the teleop part of the competition starts, that just kicks off once. And then we have this other piece here that's doing scheduler get instance run. This updates something called the smart dashboard we'll talk about in a minute. That's just, it's happening. It doesn't have to happen as fast as, my motors and my joysticks, they need attention. And so we have the continuous loop that this is my things that really need attention. So.
And the rest of the code here is basically the same as you saw in the last example, just modified for the iterative robot.
Okay.
Next, we're going to go on to a gyro sensor. We're going to start on all those different sensors, and you can see what's actually going on and measure where your robot is in the real world.
So we get to add on lots of things onto these robots. Like I said, you can go out and buy them at different stores. I mean, there's different places you can get things. Andy Mark's one of the big ones, but so there's several sensors and things like that, and sensors, as you get to build more advanced robots, if you have a beginning team, chances are what they're going to do is they're going to drive, and maybe they'll have an arm or something else that's going to do something, and that's about all it's going to do. As you get into more advanced things, you can use like a gyro and stuff like that. And one of the examples for this gyro, last year we saw how you had to drive over that 4-inch barrier, and we're like, well, okay, but the wheels they gave us were 6-inch, which means the diameter's at 3. We're going, that's not going to work with the default wheels. The radius is not going to work well. So, we're going to put big wheels on. So we asked for 8 or 10-inch wheels or something else, a little bigger. And unfortunately, we got 16-inch. So we build the robot, we build the frame, we get it up, and we go to drive it, and the robot goes like this.
It goes very nicely to the side. That's about all it does when you tell it to go straight. Time
and time again, and this happens all the time while you're building these things. You got something in your head, and then you go do it, and it doesn't work the way you want. But so we're thinking about it, and we're going, well, why does it do this? Well, I wish we didn't wire it right. Well, no, the wiring. Yes.
Quick question.
Oh.
Isn't there like a diagnostic program just to make sure?
We'll talk about that in a minute. Yeah. Well, the wiring's wrong. Well, no, the wiring was right. Okay, so the programming's wrong. So we go look at the programming. No, programming's right. And, so we're kind of puzzled at this, and we're very consistent that, we just turn off this way. And so we pull out the multimeter and go test it on the motor controller. So the motor controllers, send a control voltage through that goes up and down and tells those motors how fast to go. Well, we have 2 motors that are always going forward, right? But I also, because my motors are facing out like this, 2 are going forward and 2 are going backwards.
And unfortunately, the motors can spin very fast forward. However, the motors are not capable of spinning as fast backwards as they are forwards.
So we found a different voltage coming on our reverse. So what's happening is, well, it was giving less going backwards at certain speeds, up to 25%. We're like, how is this possible?
It was giving less going forwards.
Oh, okay, yeah. Anyway, but there was about a 25% difference at some points in time. We're like, how is this possible? Well, we got to thinking about it, and the default set of wheels they usually give you are 6-inch wheels. So you have a much smaller diameter. We've always had this problem. We just never realized it, because the robots kind of drive, might drive a little off to the side, but since I have a joystick, you always correct it, and you think that's human error. Well, actually, no. There's a slight difference in how fast the motors go forward versus how fast they're going backwards. But it shows up when you put a 16-inch wheel on there and have this huge diameter. All of a sudden, it shows up. So an example is you might take a gyro to it where we'll set it up, and once again, they've done a nice job of coding this. We put in a port. We reset that gyro, and we set some sensitivity. It takes a little tuning. When I first set it up, it was oversensitive. So so you play with the sensitivity a little bit, and then all you basically have to do is you just say gyro get angle, and it tells me. So this particular gyro is basically just telling me 360 degrees where oh well, your robot's going off this way or you're going off this way. You want to bring up the video on that one?
Mm-hmm.
So when you get the new 16-inch tire, Did they come with the kit or did you buy yourself?
Well, the drivetrain came as part of the kit. The wheels were something we just went out and bought at a hardware store or whatever. Part of the reason was we were trying to do 3 teams with similar robots, and we had to buy a lot of wheels. We couldn't find a lot of them, and so we ended up with this really big wheel that was bigger than we wanted, and that just ended up causing a problem we had never expected.
One of the things you'll want to note is that when you actually go to load up the robot, I didn't turn it on, you'll want to go under this diagnostics tab right here. And right here, it'll list all the different things that you can connect up to it. So, like you can hardwire right into the robot, or you can have a wireless radio in the bridge, the robot itself, and then FMS stands for Field Management System. That's only actually used at competition, so you don't need to worry about that unless you're at competition. So we'll run through the video.
So it's not a terribly exciting video, but you'll see a few things happen. You're starting to see some of the lights light up down here with the DS radio and the bridge and the robot. It can see our joystick. So those are coming. And then the important things, now we're talking to the robot. Now the robot code's been pushed over. And what you'll see. So I have a gyro in my hand while I'm doing this, and I'm just turning it like this. Now you see this number, just this really big number out there. Well, it's a decimal point, so it's not moving as much as it looks like it is. It's really just going, 60 degrees this way or 60 this way. But yeah, we're just taking that gyro and moving, and that's all. That's what all the code took to get that to happen. Now, the next trick obviously is implementing that in your robot to make it useful. But okay. Yep. Okay. So we did that. There's a couple others later we can cut out. So, so we're just going to cover these next couple. They're similar to the gyro. An accelerometer. The difference on an accelerometer is that I have left and right, so I can see how much movement and force I have going left and right, or forward and back. So X, Y, and then there's basically a tilt, which is your Z axis. And so an accelerometer is a nice thing because for example, on the ramps, it could help you figure out if you're actually getting up balanced. The kids are out there trying to do this manually and see this, lots of excitement going on, and it would, it really would have been nice to have a button you just hit and it would just drive it up and got to where it balanced and just quit. Because half the time they get up on the ramp and they're on the middle, except for they went over a little bit and they back up and they go over, or they tilt it, they tilt the robot off the edge or something. But an accelerometer is another type of sensor that's kind of helpful. They haven't been completely successful. They've had some problems, and they had one 3 years ago that was an analog, and then they had a digital one, and I've heard varying things about how successful they've been to get this really working well, but it's a nice sensor that is useful. So let's just go on to, so an ultrasonic sensor, this is where we had a question earlier where, once again, pretty simple. You're just setting up and giving it the channels that you're plugging into, and this is going to get us our range in inches. So there's how you tell how far you are away from things. You might take, some people had a couple of them on there or whatever to figure out where they were. They can get really inventive. What they used them for this last year a lot, so the ultrasonic, you had to shoot a basket. Well, if you're going to calculate your basket shot, a lot of people are trying to do it manually, and they make some. I guess they made maybe 10 to 20% if they were really good at it. But if you're trying to shoot a basket on this robot, even if you're driving by joystick, the best way to do it is you got to get your distance to the wall. You also use a camera that's going to capture the vision target to figure out which basket you're aiming at, and then you can calculate. You can make a calculation about how fast this ball needs to be coming out to actually hit the basket. And there were some that were really good at it. They could make, they probably made 70-80% of their baskets if they were lined up right. So that'd be one place where you'd use an ultrasonic.
We also had a question earlier about actually tracking in real-world terms of how far you're going. This is where you can actually pull in the use of the encoder.
Okay. So in this one, so an encoder is something that we put on usually the drive shaft of the wheels or a shaft on the drivetrain, and the encoder is capturing the turn of that shaft. And knowing that, we can figure out how far something has driven. So we set this up, and we set up the motors and everything, but then we turn on these encoders. And using that, if you scroll down just a little bit, we happen to know that using this distance, we travel so far. And down here, basically what happens is it basically is adding the left and the right encoder together, because they're not going to be, usually what happens is they're not exactly the same. They might be fairly close, but when it gets over 60 inches, it's going to stop. So this is how you might do a sensor that allowed you to drive so far and then stop, or take on your next command. So I talked about the command-based robot earlier. The command-based robot, Brandon, if you want to expand the commands and the subsystems also. As you can see, what I've done here is a really, really simple command-based robot. It's got a lot more classes in it. But what they've done is put together some pieces that deal with the things like I was talking about. Well, you might push the trigger. If you have something that takes a long time to run, you push the trigger and it doesn't detect it, and something doesn't happen. They put together some nice pieces to help kids build robots. So while this is more complex, this robot actually can help them build a robot and not have very much knowledge, as we'll see in a minute. They've actually made a tool that will even build a lot of this for somebody if they wanted. And now, so this command-based robot extends an iterative robot. We saw that one before. There's not like a different class that it's going to extend, but it's just building on top of that iterative robot. So we have the same things, like we have robot init, and we have autonomous init, and autonomous periodic, and the same pieces that we had before. The difference is, so we have the drivetrain subsystem on this one, and this is a super simple version of it. So you define a drivetrain, which is a specific piece of equipment that's going to run, and it's basically the definition of the devices on the robot is what a subsystem is. And then once we have the subsystems designed, we can go create commands. So for example, we have a drive with joysticks command. And you'll see in this drive with the drivetrain subsystem that there really isn't much here. It's just kind of setting it up. Drivetrain subsystem. Yeah. Okay, yeah. Anyways, let's go on to the drive with joysticks. Sorry. Okay. And then, so we get into the drive with joysticks, and we just say, well, it requires this subsystem. And the reason it requires this subsystem is, say I have an elevator, and I'm lifting something up and down, and it's going up, and smack in the middle of that, I decide, oh, I need it down again, and I hit a button to go down. Well, now it's got two commands, and it's got to figure out what to do. And so one of the things that they've built into this command-based robot is the ability to handle the commands correctly so that the robot's not getting messed up. And a good example of it is sometimes you have two joysticks. You'll have two driver, you have a driver and somebody operating a joystick, and they can, maybe they both can make that elevator move if they need to or something, and they both hit it at the same, something where it's getting two commands at once. Well, this command-based robot behind the scenes knows how to do it. And you can go look at the source code in WPI Live and see what they're actually doing there. So it gets, this is just gets the subsystem, and then it just sets up the arcade drive, and that's really all this command does. And so it's pretty simple. A lot more a lot more classes, but it's simple what it gets started. Now there's a shoot ball command. This is just another command, and all it's really going to do is shoot the ball. I really didn't do anything here. I just said what it's going to do. Now the other pieces that are important is you go up to robot map, and this is just defining all the ports for things that you have. And then the OI, the operator interface, is now where you're going to set up joysticks and things like that. And what you'll notice is a little different change. Before we got a joystick, we had to say get a raw button and all that. Well, they have a little bit of new functionality where I create a joystick button object, I pass in the button, and now I just say button when pressed, execute this command. And so it's actually a nice way to, it takes us another step in teaching these kids a little bit about some object-oriented programming and how and why this is better. Before this one, we were often doing the simple robot and some of that, and it got a little complex because you're trying to deal with these static objects all the time. So there's some nice design features in this, and it's actually fairly simple. to work with. So let's go on to the next one, Brandon. Yeah, just do close all. Yeah. So this next one's another command-based robot. Let's see. And this is actually based on one of the examples, the Gyroscope example that you'll find under the samples, where there's a whole lot more commands and drive systems here. So I've got a claw in the subsystem, I've got a drivetrain, I've got an elevator. So what this robot did, so it had an arm that was going up and down basically on an elevator, and it's got I think it was 2 years ago, the competition was they had some inner tubes that were about this big, and they had to pick the inner tube up and lift it up and hang it on the wall. So this arm would come down and the wrist would turn down so it could grab the inner tube, and then it would come back up and then hang it up. So there's some basic pieces to this. So on the claw, Brandon, go up a little. And so it's basically just setting up a motor to run this claw. You're setting up a default command here. Let's see, close, keep going. Okay, so this one's not doing too much. So go to grab.java. Okay. Oh, sorry, wrong one. We'll go to OpenClaw. Okay, so OpenClaw, basically all this is doing is just opening the claw. It's just a single command. Now if we go back to the grab command, a grab is a command group, and what it allows us to do is add multiple commands. So we can have something that opens up, we can run sequential commands, but we can also run things in parallel. And one of the things about when you're writing this code, what the command robot solves is I may have a subsystem that's moving the elevator up, but basically all I've done is tell a motor to move for so long. Well, I have some time that motor's basically sleeping, and another thread can kick off and do something. So rather than having to teach the kids how to do that by creating these commands and them doing some stuff in the background, I've started that elevator up. It's lifting the robot up, and something else can be going on, like moving the wrist up to where it needs to be to move up, and then it'll move it so that it can hang the inner tube on the wall. So, and then let's see. So go to soda delivery. I think that one. Yeah, so here's a place where they're just doing all sequential in this command group, where they're just saying, well, prepare to grab. So it's getting it down, ready to grab, creating a new grab, driving some distance with it, and placing the soda somewhere. But it's just all sequential commands. So we have commands, we have command groups, and we have subsystems. And that's really the core of what this command robot takes to run. Now, let's see, so go up to Gearsbot and scroll down. All we really did to get the robot running was just say, well, init some stuff, set up our autonomous command, and let's see, set up the autonomous command to run and go do that. So the soda delivery would just happen on its own. And it doesn't take much to make this run. Now I'll show you a nice way to make one. Okay. Okay, so okay, gotcha. Okay, so they made a nice tool to actually build this. So when you get those students that actually aren't programmers, where am I at, right? Why don't I have, oh, okay, it's here. So they made this robot builder tool. So when you have students that aren't programmers and you're trying to build this out, it takes a little while. They actually built this tool that will allow you to go create like a subsystem. Whoops. And I'm not going to really give it a name. I'm just going to kind of throw some stuff on here really quickly. But this robot builder tool is really a neat little tool, especially for your kids that have never done this and you're trying to give them an idea about how to build the robot. It doesn't do everything for them. It still makes them code some. And so basically what I've done is I've dragged I've created a subsystem on here. I've dragged a robot drive on here. I can choose which one I want to run. And I can go up here and I can just tell it to generate the code. And it'll create the buttons, it'll create all the pieces. This is really a nice tool for beginner teams. They can generate about 85% of the code. And then you can start teaching them about that code, and they start to understand it a little more, but it makes a nice command robot that'll run. It'll do almost everything for you. So, a very nice tool. Okay, so close that and go on. Yeah, you gotta go. Okay. Yep.
We still gotta do last questions.
Yep. Yeah. Well, we've done some of the first ones, but yeah, I get what you're saying. Okay. So the question was about debugging earlier, and how do you debug this? So there's a few ways. There's something called the Smart Dashboard we'll talk about in a second. There's the just doing a system out println in NetBeans, which is kind of useful, and then the driver station itself. You can also, we'll talk about all those in just a minute. The other thing that I'm just going to touch on real quickly is you can use the debugger in NetBeans. You plug it, but I suggest what you do is plug directly into the CRIO. Usually you're running over some routers that connect together. You connect directly into that CRIO and step through. The directions make it look like you could run it wirelessly, but it doesn't seem to work very well. But it's a nice way if you're really writing a complex robot. But most of the time you can do a lot with the Smart Dashboard and just doing system out printlns. Let's go to, let's see, so driver station logging real quick. Okay, so scroll down to the piece. So the driver station logging, we'll show a real quick video on that. All you do is basically get a driver station object, and then you just do a print line. The problem with this is that each line is only 21 characters long. I don't know what's with that limit, but that line, so you have 6 lines that are only 21 inches. It can be helpful. Yeah, that one. Okay, so you see right here, the number just changes or whatever. So you get 6 lines here, and it's just 21 characters. I don't know what that limit is, but it can be helpful because this is what you have running possibly when you're in competition. The piece above it, the Smart Dashboard that we'll talk a bit more about in a second, is the better place to do this. So go ahead, close that one. And let's see. So system out println, go to the other video next to it. That one? Okay. So if you're running NetBeans, you can just say system out println. And if you see down here a little bit, you'll see robot debug message line 1. And then you'll see robot error message. It does not change the color or tell you that it's an error message, but it just does the same thing. But you can, if you have NetBeans running, which you don't usually during competition, but while you're building it and everything, you can just output here. And that's probably the preferred and easiest way to do this. So. And then let's go to the ANI dashboard real quick. I'm just going to touch on this real quickly. I got to pick up a little speed here. So actually, Brandon, open up the, click on the ANI dashboard down below. Okay. And then the little first one, yeah, that one. Okay, so this is the ANI dashboard. It comes with the lab view, and there's a sample in here, and I'm not going to go into this code because I want to get onto a couple other things real quick with Vision. But this doesn't update without you sending some stuff to it. So if you go to NetBeans, let's see, yeah. If you go to NetBeans and you do one of those samples, if you go under New Project and Samples, there's one that shows how to update the dashboard. And it's got all kinds of interesting, add cluster and all this because you have to pack it right for LabVIEW. And that's, it just has to be done that way. We've tried to play with it a little and just didn't have a lot of success. So, yeah. So it'll run, and if you push all this stuff out to it, it'll go and you can see things starting to move up there, and it gives you some basic feedback that can be useful. Let's close this up because we're really running behind. Okay. So go to the Smart Dashboard send data. Yeah, robot template. Okay, scroll to the bottom. Okay, the Smart Dashboard is this piece we're going to look at in a second. It's been kind of the piece up top here. All I had to do was say Smart Dashboard, put double, and then I can start feeding it stuff. And this is running on the robot, and it will push it back up to the Smart Dashboard so that you suddenly have data about what's running in it. The cool thing about it is it just shows up on the Smart Dashboard for you. So Brandon, if you, and then, yeah, if you run that video real quick. So what's going to happen here, I have to reveal them because I had them and removed them for some other stuff. So all I'm really doing is a loop, so it's kind of going back and forth between true, false, and then the ball shooter speed is just incrementing by 1. This is the Smart Dashboard up here. It's a Java dashboard, so you can write different code to, you don't have to write any code. The part to do here, all I did was put code on the robot, and I got this nice little graph about what was happening. I can add some, I can create dials, and all I did was put code on the robot, but I can also extend this Smart Dashboard, and you'll find this on the First Forge website. I get a nice little ball shooter, and all I've done is just go to the Smart Dashboard and say, hey, change the field type to something else, and that place in the code where I showed you where I said, you know, put double, put string, put Boolean was all it took. So the Smart Dashboard is a really nice tool for troubleshooting and just knowing what your robot's doing a little bit. Let's see, so go to network tables. Network tables, so you have your, huh?
Tables robot.
Sorry.
There's 2 of them.
Oh, okay. Open up the dashboard one, the one that doesn't say robot. Yeah, that one. Okay, network tables is something, so you always have this, you want to talk from the dashboard to the robot, and there hadn't been as many good ways to do this until recently when they added this Smart Dashboard. And the first thoughts out of your mind is probably just write a socket, send the data over, or do some other post. And you certainly can do those tools, but they're a little harder to teach kids about, well, okay, let's write a socket, let's, you know, buffer all this, or make sure we don't have 2 things coming in all at once. And so they created this thing called a network table. And so you'll see, let's go up a little. Okay, yeah, so you see where I say just get table of this name. Well, if it doesn't exist, it creates it. And I can put just basically primitive types on this. So I'm saying like put Boolean found, and maybe this is a targeting system, and it says, oh, I found the target. And I can put it in this network table. I can do this in a transaction even, where I'm sending these 3 things, and all 3 things will have to be updated before anything else can get it on the robot side. So there's a network table on the robot, and there's a network table on the Smart Dashboard. And the Smart Dashboard, so go up a little bit. The Smart Dashboard, we can create widgets for the Smart Dashboard just by extending static widget. There's some nice documentation out on the First Forge site about how to do this, but basically all you have to do is extend static widget. Static widget extends JPanel, so basically swing. Anything with swing you can add into this, and you have a really cool dashboard you can do stuff with. You don't have to do any of that. You don't have to create a new widget, but you can just push the data to the dashboard. But if you want to go add stuff in, you can. But anyways, these network tables are a nice way to push data back and forth without having to go out and teach students about sockets. Now it is, I will say right now, I've done this and it's a little slow. Probably there's a 1 to 2 second lag when it runs. But for this coming year, they're rewriting it, and it's supposed to improve it by hundreds of %. So it'll work even better. So let's see. And then, let's see, what are we looking at? Okay. Well, I'm going to cover a couple things about vision real quick. So just jump down to the vision ones. So you can process vision in a couple ways. One, you can do it on the robot. And the other one is you can push it back to the Smart Dashboard and process it. And so the vision, you saw the targets. And real quick, I'll give you an idea. So you have this light. This was white as you saw before, and you have this little halogen light. And when you point it at this at a certain angle, if you're looking at it, it just lights this up like you wouldn't believe. So the cameras can take the images, and what they'll basically do is they find that lit part and they subtract everything else out of the image, and now they can find the squares and they can figure out the center point of them. So real quick, we'll show you. And once again, this is something that's in a sample. It's in one of the samples. Every year when they do these different games, they put out sample code about how to do vision targeting and stuff, and then you can just extend upon that or do more. So this one, basically you have a network camera that's running on the robot, and the C-Rio gets that camera instance. It goes out and you set up some measurement types, basically to help start finding the squares. In this one, I'm really just processing a single image and I'm going to find the squares. What it usually does is you take the camera, you'd save the image, and you'd process each one as you save them. Or you just take the picture and process them. But it goes out and it keeps only the red objects, as you'll see here. So you've got to tweak this a lot, though, to find exactly where you want to be. And you